a session for you today called Playing Sudoku on Graphs. So we're going to look at investigating Sudokus and investigating graphs, but not necessarily as you know them.
Thank you very much, Rebecca. It's lovely to be with you all in Scotland today. Happy Maths Week. I'll just share my slides.
And before we get going, it'd be nice for us to just see where everyone is, what school they're coming from, where they're located. I'm in London, James is in Norfolk. Why don't you put in the chat box just to get to know each other where you are at the moment and see if anyone is just around the corner from you.
Yeah, that would be nice. Although technically I'm on holiday in Norfolk. I'm normally Milton Keynes. Everybody's waking up. Can you see my slides all right, Rebecca?
Yeah, I can see them. Thank you. Do you want to move on to the next one? Because we've got a fun starter to get people thinking, haven't we?
We've got some Ireland and from Aberdeen. Hello, both. Excellent. Well, let's make a start. You can carry on leaving your comments in the box. But as Rebecca says, I'd like to speak to you today about something that will be familiar to all of you, Sudoku, but maybe in a context that you wouldn't expect. Let's begin with an exercise. I work in the field of graph theory, and these two are examples of graphs. They're vertices connected by edges. You could imagine it as cities connected by roads. Here we have a 6 cycle on the left and a 5 cycle on the right. So 6 and 5 vertices respectively, joined up cyclically by edges. Okay, so this is the puzzle I want to get you to start off with today. What I'd like you to do is color in the vertices such that no two adjacent vertices receive the same color. So I don't want 2 red vertices, for example, with an edge between them. And subject to that, I want you to use as few colors as possible. So can you tell us in the chat, please, how many colors you need for the graph on the left and for the graph on the right? It may not be obvious how exactly this is connected to Sudoku, but all will become clear in 15 minutes or so. So to reiterate, you need to color in the vertices with as few colors as possible, such that no 2 neighbors on these cycles have the same color. And technically speaking, that's what is called a proper coloring in graph theory. And the smallest number of colors is called the chromatic number. So try and remember that if you can, but don't worry if you don't, as we'll repeat this a bit later. So has anybody got any ideas? Guesses are allowed. So if you take a piece of paper and do some scribbling, you should be able to find a good coloring quite quickly. Well, as a trivial example, I, on the left, could take the 6 cycle and color each vertex with a different color. So it's going to be less than 6, as that's quite a clumsy coloring.
We've got Gandar. Oh, there you go. You've seen it too. Gandar says 2 and 3.
2 and 3 is absolutely correct. Well done, Gandar. Okay, I'll show you the answer. So on the left, because the cycle is of even length, we can alternate colors, red, blue, red, blue, red, blue. But because on the right, the cycle is of odd length, I can't do that trick. We're going to end up with two the same color. So I'm forced to use an extra color here, which in this case is green. What that means is the chromatic number of the 6 cycle is 2. The chromatic number of the 5 cycle is 3. Okay, let's move into Sudoku then, and just keep this in the back of your minds. Okay, here's a Sudoku puzzle. I dare say you've all seen this. How many of you have played Sudoku, by the way? If we have any Sudoku enthusiasts, shout out. But the idea is we start with a 9x9 grid, and we have a partially filled in grid here. That's the puzzle. And the goal is to fill in all of the fields so that all of the numbers 1 to 9 appear in every row, in every column, and in every 3x3 subgrid as well. So for example, if we look at the central entry here, I can see that everything apart from 5 occurs either in the column, in the row, or in the middle 3x3 subgrid. And so I can just very simply fill in a 5 there. And similarly, if we go below, I can fill in a 3. In short, this is a very easy puzzle. And I'm not going to complete the puzzle with you today, since that would take a full half hour. But I'd like to ask you a question, please. Is investigating Sudoku mathematically the same as playing Sudoku? What do you think? So I just said I'm not going to be filling in a Sudoku puzzle with you today. How does analyzing Sudoku mathematically differ from merely filling in a Sudoku puzzle? Or would you say the difference lies in? Any ideas? Is filling in
Because there's a bit of a delay for the YouTube stream. While we wait for other people to answer, I'll just give my answer. And I think that it is very different because you could start to think about the different ways that you could make a Sudoku puzzle. But when you're actually playing a Sudoku, you're just kind of focusing on one Sudoku and the solution for that one thing, aren't you? But if you're investigating a Sudoku, you're perhaps looking at why it looks like it does or whether it could look any different. So I think investigating it mathematically is a bit different. I wonder what other people think.
Yeah, that's very good, Rebecca. Actually, we could draw an analogy maybe with number theory. If you're thinking about individual numbers, you can enjoy their individual properties, find curious patterns, or just add up a long list of numbers. But is that the same as doing number theory in mathematics? Not really. In mathematics, instead, you're not looking at just individual numbers, but you want to say something about all numbers. So I think I'll move on to the answer. Mathematics allows you to say something interesting about all Sudoku puzzles, not just individual puzzles. So that's the advantage of analyzing mathematically. And to show the difference, and I'm going to perhaps alienate my audience a little bit here, I don't really enjoy Sudoku, and I've never played a puzzle in my life. But that doesn't stop me from analyzing them mathematically, which I do find interesting. So if I quote here Gary Maguire, and you'll find out why he's important in the story later, he said, "I still find it a nice way to relax now and then, but to be honest, I prefer doing the crossword." So he's the big guy in Sudoku mathematics. I'll just give you a little bit of history. Some say that this originated with the mathematician Euler. Really, he was working on Latin squares, which have the property that all these numbers appear in the rows and the columns, not necessarily the subgrids, but he certainly didn't think of them as a puzzle. But in the 1890s, there were French newspapers who had puzzles very similar to Sudoku. Actually, technically, if you know what these are, they were based on magic squares, not Sudoku. But it first began to be published in Dell magazine in the USA under the name Number Place. So surprisingly, it isn't Japanese originally, despite the name. Okay, why does it have a Japanese name? Well, it was introduced to Japan by the president of a puzzle company, and it was named. And please excuse my Japanese here. If anybody speaks Japanese, it was called Suji wa Dokushi ni Kagiru, shortened to Sudoku, which means all of the numbers have to be single. But there was a judge in Hong Kong who really loved that puzzle and introduced it back to the West. He created his own programs and got them published in the Times eventually. And as you know, everybody knows about Sudoku now. Okay, next question. Well, I'll ask two questions together. What are the requirements for constructing a Sudoku puzzle, would you say? And what makes a Sudoku puzzle hard or conversely easy? So imagine you're trying to create a Sudoku puzzle. You can't just put any numbers in the grid at random. What do you need to take into account when you're creating a puzzle? And if you're trying to make a hard puzzle, how would you do that? So, for example, if you were trying to make it very easy, you could fill with all start with all of the grid places filled in already. That would be extremely easy.
We've got a school in Aberdeen have said that it's harder when there's less numbers showing.
Excellent.
That's like what you were just saying, isn't it?
Yes, perfect. Yes, that was one. In fact, that's really what we're going to be speaking about today. More numbers, so you have more to work with. Yeah, that's the converse. Yeah, so if I have just one gap in the Sudoku grid, you can fill it in straight away. That's trivial. Okay, when you're designing a Sudoku puzzle, there are two principles you need to bear in mind. Firstly, it needs to be possible to complete it. Otherwise, you'd have a lot of frustrated readers. And secondly, and this is a little bit more subtle, there needs to be exactly one solution. So from your partial grid, the clues, there needs to be just one way to fill in the rest of the puzzle. Also, as Aberdeen correctly says, the smaller the number of clues, in general, the harder the puzzle. A bit more subjectively, you could think about which techniques you use to solve the puzzle as well. Some have created, well, I'll show you an example. This is a Finnish mathematician, Arto Inkala, who created this puzzle with 23 entries, which has a reputation of being very hard. And he designed this because it doesn't have the smallest number of clues you can have, but you can't attack it using just straightforward techniques that others can use. However, apparently an experienced player could finish this in less than 20 minutes. Okay, but let's ignore maybe that aspect of it and instead think about the smallest number of clues we can have. Now, there are lots of puzzles known with 17 clues. In fact, there are about 50,000 of these known now, but nobody could find one with less. So it's conjectured that 17 clues is the smallest possible you can have in a Sudoku, such you can complete it uniquely. The book Taking Sudoku Seriously said the following. This is about the problem of finding the smallest number of clues in a Sudoku puzzle. If you can figure it out, you'll be a rock star in the universe of people who care about such things. Granted, that is a far smaller universe than the one full of people who care about actual rock stars, but still, it would be great. Okay, why is this a difficult problem? Well, the number of Latin squares, that's without the restriction on the subgrids, there are this number of Latin squares, about 5 times 10 to the power 27, so a lot. The number of Sudoku boards is a lot less. So it's about 3 times 10 to the 12, in other words, a 3 followed by 5 and another load of zeros. So this number here. So still a gigantic number, but only a small proportion of the Latin squares. So you might think you could attack that by computer easily. However, think about the following. How within a completed grid can you find the smallest number of clues that were completed? Some of them have different numbers. Instead, you've got to think about all the possible ways you could begin by deleting clues. And you want to get to a configuration, which I'll call a minimal configuration, such if you delete one more clue anywhere, you end up with a board that has more than one completion. Okay, so here's the complicated bit. The sequence and the clues you choose to delete from your completed board would lead to different minimal configurations with different numbers of clues. So for each of these 3 times 10 to the 12 boards, you've also got to consider all the different ways of deleting the clues. So there are obviously 81 ways you could start with deleting 1 clue, but then deleting 2 clues is 81 times 80 divided by 2 different ways of doing it. And then if you're looking at deleting 3 clues, 81 times 80 times 79 divided by 6, and I can probably, you can imagine that this is going to grow very quickly. So this is definitely not a simple problem. But in 2013, the problem was solved by Gary Maguire, the guy I quoted earlier, and it turns out that 17 clues is as small as possible. It took 7 million hours on a computer to do, because they were working in parallel. Okay, so let's move back to graph theory. You remember our example at the beginning. This is the example we're going to use to motivate it. If you take, perhaps you've heard of the 4-color theorem. If you take any map of countries, you want to color the countries such that any 2 countries which border have a different color. And it turns out that all you need to do that is 4 different colors. So here's an example of a map of the states in the US, all colors so that bordering countries have different colors. Actually, proving that result was very difficult, and it was done using graph theory. Let me just define these properly. A graph is a collection of vertices connected by edges. So these are the counties in Germany. We can represent each county by a vertex and join them 2 vertices by an edge if the countries have borders. So how can we represent Sudoku by a graph? Well, let me replace each grid square by a vertex, 81 of them, and I'm going to join one vertex to another if it lies in the same row, the same column, or in the same 3 by 3 subsquare. So for example, this blue vertex here is going to be joined to each of these red vertices. And that can't have the same entry. The blue one can't have the same entry as any of the red ones. So here's one representation of the Sudoku graph. Now this is a bit simplified. If we draw in all of the edges, then it would be a horrible mess and you couldn't see anything. So there are some edges which are suppressed here. For example, any vertex in one column has to have an edge to a vertex in any other column and the row as well. But you can see the subgrids very clearly here. And here's a completed Sudoku board. You could do it either with colors or with numbers. Coloring them with the numbers 1 to 9 is the same as using a different set of colors. It's all equivalent. So this is a completed Sudoku board in the form of a graph. Okay, let's see how we can generalize this. That's something that mathematicians love to do. So let's not just look at the Sudoku graph, but any graph. Here's one famous graph called the Peterson graph. And it turns out that I can color the vertices of this graph with just 3 different colors, such that no 2 neighboring vertices receive the same color. So its chromatic number is 3. Okay, let's see how we can play Sudoku on this graph. This is a Sudoku coloring. Why? Because it's possible to complete it to a proper coloring of the whole graph, and there's just one way of doing so. So Rebecca, could you see my pointer, by the way? I don't think you can. Yes, you can. Okay.
Yeah, I can.
Okay, perfect. So how can I fill this in? Well, if we look at this vertex down here, it's got both a blue neighbor and a green neighbor. So there's only one I can fill it in, red. Next, if I look at this vertex here, it's got a red neighbor and a green neighbor. So I've got no choice except to color it blue. There we go. And carrying on this way, I can deduce that I can color the rest of the graph in just one way, and we get back to the proper coloring we had at the beginning. So I've just exhibited a way of having 4 clues in the beginning on the Peterson graph, which leads to a unique coloring. So instead of the Sudoku graph, we're looking at this funny board instead. And 4 clues is the best possible. If I start with 3 clues, then there's always going to be more than one way of completing the rest. Let's look at some examples, shall we? Well, first of all, let me formally define the Sudoku number. So let the chromatic number of the graph be k. Now remember, by chromatic number, we mean the smallest number of colors, such you can color in all of the vertices and neighboring vertices receive different colors. Then the Sudoku number of a graph is defined to be the smallest number of vertices you can color in with k colors, such that that coloring has a unique extension to the whole graph. Okay, just like Sudoku, smallest number of clues. Right, let's return to one of the graphs we saw at the beginning, the 6 cycle. Now, you correctly worked out that you need 2 colors to color this in. What's the Sudoku number, would you say, of this graph? What's the smallest number of clues that you need in order to finish a 2 coloring of the 6 cycle? That's a slightly more difficult question. Again, guesses are allowed. So you need to start with a partial coloring, which has just one way of being extended, and you need the smallest number of clues. So for example, if I filled in 5 colors, there'd only be one way of completing that. That's a very trivial bound. You can do better than that.
If you used 4 colors, there's still only one way of completing it.
Okay, so Rebecca's got 4. Any improvements on 4?
Oh, Claire at
yes.
St. Joseph said there's lots of people guessing 2 colors. So if you start with 2 colors, there's one way of completing it.
Yeah, well done, Claire. Very good. Any improvements on that? Can anybody do less? What if you start with 1 color? Okay, well, I'll give Claire the award because she's closest. In fact, you can do it with 1. Okay, so we know we can fill in the whole graph with just 2 colors. So if I start by painting one vertex red, I know that it can't have any red neighbors, so I've got to fill in the next one blue. And then because it can't have any blue neighbors, I've got to fill in the next one red, blue, red, blue. So if I start from just one vertex here, paint that red, there's only one way I can complete it. So in fact, the Sudoku number of this graph is 1. And
That's
in fact,
great. And St. Joseph's did guess 1, but I think we just didn't see it in time because of the delay. Well done.
Okay. Well done. Okay, and in fact, we can say something a lot more general. A graph has Sudoku number 1 if and only if it has a proper 2 coloring, chromatic number 2. So in other words, if it has the property that you can divide its vertex set into 2 parts with all of the edges going from one to the other, so like the 6 cycle. But again, that won't work for the 5 cycle. Remember, you need at least 3 colors for that, and it's going to take more clues, quite a lot more clues actually, it works out. Yeah, so if you suppose that you've got a graph with chromatic number at least 3, so you need at least 3 colors to color it in, you can see that it can't have Sudoku number 1 in this case, because if you paint just one vertex red, then you could have one coloring completing with red, blue, and green, and then in the resulting coloring, I just swap green and blue. There's no difference between them. So if I just fill in one vertex, there's no way I can extend that uniquely. Okay, so that's why it's important that it's a 2-colorable graph. Okay, let's look at the opposite extreme, perhaps. This is a graph which we call a clique, a complete graph. Now, that has the property that any 2 vertices are connected by an edge. Okay, so here's the next challenge. How many colors do we need to color this graph? And again, we want different vertices to receive different colors. And then what's the Sudoku number? What's the minimal number of clues for this graph? Okay, so first of all, we need to know how many colors we need to use to fill in the graph. Remember, we can't have a red vertex with a red neighbor, etc., etc. So you're going to need a lot more colors for this graph. And then how many clues do you need? Any guesses? Clear one last time, so let's see if you can do it this time. Gandar says 6. Well done, Gandar wins this time. Yes, because you need to have all of the vertices different colors. Yes, you need 6 colors. Okay, what about the minimum number of clues? How many clues do you need? Well, for example, if I just delete one color, say the red vertex, then that will work because it's going to have neighbors of all different colors. So I have to color that in red again. Can I do any better? Oh, Claire is getting lots of different answers. Well, that's a good thing. What are some of the ones you're hearing, Claire? Okay, what's the smallest answer you're getting? What's the largest answer? Ah, break time. Okay, fair enough. I'll give you the answer then. Okay, so as you say, we need 6 colors to color it in. And if I delete any color, that will give us 5 clues in this case. And in fact, that's the best you can possibly do. So if I delete 2 or more colors, then I could just swap them in the resulting extension and it wouldn't be unique. Now, the interesting thing from a mathematical point of view is these are the only graphs with the property that the minimum number of clues is equal to the number of vertices minus 1. So if I delete 2 or more, then I get a non-unique extension. And just very quickly, I'll show you a proof of this fact. Now, don't worry if you don't follow all the details. Here's a sketch. So let's say we've got 5 colors here: red, blue, green, yellow, and pink. Now, it's important here that if we choose any color, say red, then we can find such a vertex which has neighbors of all the different colors. So a red vertex here would have blue, green, yellow, and pink neighbors. We can always find such a vertex. Why? Well, if there's a red vertex which doesn't have neighbors of all the different colors, I could recolor it with one of those colors. And if I just carry on doing that to all of the vertices, then I'd end up with a coloring that doesn't have any red vertices at all. But since I'm assuming here that we need 5 colors, that's obviously going to be impossible. So we're going to hit an obstruction at some point. So let's call those vertices full if in the coloring they have like a rainbow neighbors of all different colors. And let's look just at the full vertices. Now, there are 2 different cases here. Either inside the graph, they could form a clique, all connected to each other, or they could not. So here in this diagram, we're looking just at the full vertices. And you can imagine there are some other vertices in the graph hanging off the edge, okay? Now, if they don't form a clique, and I delete those 2 colors, if there isn't an edge between them, then in a resulting coloring, I can just swap those 2 without any problem. So we'd have n-2 clues in this case. And if they do form a clique, because, well, if they are all of the graph, then we're done. We know it's a clique. If not, we know that there's got to be another edge somewhere. So say this green vertex has a blue neighbor without loss of generality. Then if I delete that green vertex and the blue one, then this guy here has got to receive the color green because it can't be blue. And then I've got to paint the remaining color blue. So in both cases, we've shown that we can delete more clues and still complete it in a unique way. Okay, let me draw to a finish here. Now, mathematics isn't just about finding answers. It's also about asking good questions. That's half of the battle. What questions do you think would be interesting to explore in this theory? if you were a mathematician and thinking about these problems, what would you like to know?
I think we're almost out of time. So perhaps I'll share one of my questions, which is that
Mhm.
um, looking at the minimum and maximum number of ways of doing things is always an interesting thing to explore.
Yeah, that's always the first question of a graph theorist. Okay, I'll just ask some questions which I found interesting. And as a mathematician, well, it's not like at school, there aren't answers in the back of the book anymore. I don't know the answer, but I'd like to find out. That's how mathematics works. So which graphs have, oh, there's a misprint here, but what can we characterize the graphs for which the number of clues we need is 2 less than the order? It seems to be a difficult problem. What about larger Sudoku puzzles? We talked about 9 by 9, but we could also play it on, say, 16 by 16. It's got to be a square number if I want to divide them up into subgrids. So if we go smaller and look at 4 by 4 Sudoku, the answer is just 4. But for 16 by 16 Sudoku, nobody knows the answer, but the smallest known is 55. But nobody knows the real answer. We said that 17 clues for Sudoku is the smallest possible. But how many such configurations are there? Nobody knows. As I said, not all Sudoku boards contain a configuration with just 17 clues. What's the largest number of clues in a minimal configuration? People have found such boards with 40 clues, but it could be larger. What about other graph colorings? We've spoken just about colorings, proper colorings with vertices that are connected having different colors. But there are lots of other colorings of interest to graph theorists. For example, one that I'm particularly interested in is called rainbow colorings, where between we paint the edges of the graph instead, and between any pair of vertices, we want to find a path which is rainbow, has all different colors. So I'm interested in unique completions of such colorings as well. Those are some of the questions that interest me, and I hope some of them interest you as well. So thank you for playing Sudoku with us today.
Thanks so much, James. I hope everyone's leaving with some questions as well as ideas of what they could explore further. We've put in the chat a link to a survey. It'd be really good to have your feedback. So if you've got time to click on that, it shouldn't take more than a couple of minutes to complete. Thanks so much for joining, everyone.